everyone. We are going to get started now. So welcome to day 2 of the IAP course, Fundamentals of Climate Science and Policy. So today we'll hear, kind of building off of what we talked about yesterday, hearing about Climate Science 102 and Policy 102. So just before we get started, these are the same as yesterday, but a few expectations. So first, if you have any clarification questions during the presentations, feel free to raise your hand or your name tag. Otherwise, we'll hold questions for the end, and we'll kind of have a more broader discussion at the end of the presentation. And for those, we'll bring a microphone around just so that everyone can hear your questions. And lastly, the name tags and tents are for all 3 days of the course, so please leave those here at the end of the day. Okay, and with that, we will get started on the first half of today, which is Climate Science 102, where we'll be discussing climate impacts and uncertainties. So I am Lexia Sassoni. I am a PhD student in the Earth, Atmospheric and Planetary Sciences Department, and I study atmospheric chemistry.
Hi everyone, my name is Chris Womack. I'm a PhD student in the Department of Aeronautics and Astronautics, and I work on climate modeling.
Hi everyone, I am Shreya. I am a PhD student in Aeronautics and Astronautics as well, and I work in sustainable aviation.
Great. Okay, so we'll do a brief recap of what we talked about in Climate Science 101 yesterday. So you'll remember that we were able to kind of estimate the Earth system as a box model. So here we have kind of 3 box models with the atmosphere, the land, and the ocean. And so much of our discussion focused around this kind of energy balance of incoming radiation from the sun and outgoing radiation coming from the Earth. And so we learned that the atmosphere plays a very important part in modulating this energy balance. And so things like greenhouse gases and aerosols are able to affect this outgoing radiation, which helps to dictate the overall temperature of the Earth. And so we ended the day yesterday by kind of concluding that the most recent warming that we're seeing as a result of increased greenhouse gases in the atmosphere is a result of human activity, anthropogenic activity. And so today we have a few intended learning outcomes. So hopefully by the end of this presentation, you'll be able to explain the major impacts of climate change, the physical mechanisms that cause them, as well as the associated social and economic costs. You'll be able to describe the key components of climate models and summarize the processes that they can represent. And finally, you'll be able to identify major sources of uncertainty in climate projections and evaluate how these uncertainties influence climate-related policy decisions. So these are kind of the goals for today. Okay, so I'll start with talking about the Paris Climate Agreement. So we referenced this a few times yesterday, but I don't know if we actually explicitly defined it. So the Paris Climate Agreement is essentially an international agreement among different countries and parties with these kind of 3 main goals. So the first goal, which I think it's best known for, is for limiting the average global temperature increase to below 2 degrees Celsius. They kind of have this sub-goal of pursuing efforts to limit it to 1.5 degrees. The second goal is to kind of enhance resilience and adaptation to climate impacts, which kind of relates to our policy discussion yesterday. And then the third goal being aligning these financial flows globally with these objectives. And so before I talk about climate impacts, I want to hear, you guys feel free to just call out what comes to mind when you all think of climate impacts. So feel free to just call out. Yeah.
Frequency of severe weather events?
Yeah, frequency of severe weather events. Great. Anyone else?
Impacts on food systems?
Yeah, food systems. Great. We'll talk about that. Yes.
Rising sea levels?
Yeah, rising sea levels. Yeah, so all of these things we'll definitely touch on, but great. So I think oftentimes when we think of impacts, we usually think of kind of impacts directly on the climate system, but I guess food systems, we kind of talk about cascading effects, which we'll get to, but Climate change, I think, as most of us think initially, is usually related to changes in Earth's temperature, right? Global warming is kind of the initial effect of those greenhouse gases. And so what I'll do now is I'll walk through this figure that comes from the 6th assessment report from the IPCC. And so what it will show is, kind of nearest to me, it'll show the different climate change effects, the different impacts that we'll talk about. And these different columns will represent different degrees of warming. And so remember, thinking back to that Paris Agreement, we have a goal of staying under 2 degrees Celsius of warming with a sub-goal of reaching 1.5 degrees Celsius of warming. And today we're already at around 1.1 degrees Celsius of warming relative to pre-industrial times. And a sort of business as usual, we're likely to hit this extreme scenario of 4 degrees of warming. So these are kind of the different scenarios in terms of the average global warming that we'll see. But you'll see our first impact that we'll talk about is actually extreme temperature. So not just the global average, but temperature extremes. And so here we'll see the hottest day in a decade. The temperature of the hottest day is expected to increase with climate change. And so already we've seen 1.2 degrees Celsius warming in our hottest days that we're experiencing. But that could get as much as 5 degrees Celsius warmer for our hottest days. And so just to give you a little bit of reference for Boston, assuming Boston is warming kind of as the global average. So our hottest day in this decade was this past summer, and it was 102 degrees Fahrenheit. And so if we were able to kind of meet that Paris Agreement, stay under 2 degrees Celsius, that day could be as hot as 104.5 degrees Fahrenheit. And in a worst case scenario, 109 degrees Fahrenheit. And so these extremes are really dangerous, especially for people who are experiencing pre-existing health conditions. And so this really impacts human well-being. Another impact that we expect to see is increase in the frequency of drought. So a drought that used to occur once in a decade now is occurring 1.7 times more than pre-industrial times, and that could get as high as 4 times more under an extreme warming scenario. And so I'll talk a bit about the mechanism behind why we're seeing this, and this all ties back to essentially the water cycle. And so here I am showing 2 variables having to do with the water cycle. So one is evapotranspiration and one being precipitation. And what I'm showing here is the expected change under a kind of intermediate warming scenario. So we'll start with panel B. You can see a lot of red here, which shows we expect globally in most regions of the world an increase in evapotranspiration. So essentially you're getting evaporation of water from the surface, and that leads to increased drought conditions. And then you can see precipitation has more kind of regional variability. But in the areas where you see those brown colors, those are areas where we expect to see decreases in precipitation. And so in those regions, especially, they're going to be highly prone to drought as a result. So next up is precipitation. You got kind of a brief sneak peek of that. But in terms of precipitation, we expect our extreme precipitation to increase with warming. And so, again, what used to be a wettest day in a decade now happens already 1.3 times more, and that could get as far as almost 3 times more under an extreme scenario. And so the mechanism behind this is the Clausius-Clapeyron relation. I won't go through all the derivation of how we get there, but essentially with what this shows is that we see a 7% change in our saturation vapor pressure for every degree Celsius of warming. So basically, in plain terms, that means that warmer air holds more moisture. When you have moister air, that will lead to increased precipitation. We also are going to see a change in our snow cover. So this is expected to decrease globally. Again, we're already seeing some decreases, but it could get, under an extreme scenario, almost minus 26% compared to our current snow cover extent. And so the mechanism behind this is pretty straightforward. It's basically caused by earlier onset of snow melt paired with the warmer temperatures that we'll experience. Tropical cyclones, I think someone mentioned that when they were thinking about impacts. So again, we're expected to see the proportion of intense tropical cyclones increase under our warming scenarios. And so to get a tropical cyclone, you kind of need these key ingredients. So you need a pre-existing low pressure disturbance, you need warm sea surface temperature, high relative humidity, weak vertical wind shear, and the Coriolis force. And so under climate change, we expect, especially bullets 2 and 3, we expect our relative humidity to increase and our sea surface temperatures to increase. And so this is really what's leading to that increase in intense tropical cyclones. And the last kind of impact that we'll be talking about is sea level rise. And so you'll see under each scenario, we see kind of 2 different estimates. This is because sea level rise happens on a lot longer time scales. And so we'll see for each scenario, you have a 2,000 year and a 10,000 year estimate. So these are the time scales that it takes for the both meltwater from glaciers and ice sheets, as well as thermal expansion of seawater. So this is kind of the time scales that this happens over. And so these are, you can see in the 10,000 year commitment, we could see like 7 meters of warming under a kind of conservative scenario, and maybe 33 meters under a real extreme scenario. And so these, again, are global average impacts, but as we saw when we were looking at the map of precipitation, this is important to think about what's actually going to happen at the regional level. And so here, what I'm showing is a plot that basically goes from browner colors, where the regions will become hotter and drier, to the more dark purple colors, which are regions that are going to be hotter and wetter. So we can zoom into 2 kind of example areas. So one is the western United States. And so in this region, we're expected to get hotter and drier conditions. And so this is conducive to things like wildfires, which we've already seen an increase of. And you can compare that to somewhere like South Asia or India. And here you're getting hotter and wetter conditions, and so you might be more prone to things like flooding in this region. So it's really important to think about these regional impacts. And it's also important to note, so on this scale, you're seeing a lot of these darker brown and darker purple colors. A lot of that is taking place in the tropics and the global south. And so it's also really important to think about equity in terms of who is kind of causing these climate change impacts versus who is actually experiencing the brunt of the force of these impacts. Yeah, so that's kind of overall the impacts on the climate system itself. But as someone mentioned before, there are these different cascading effects into things beyond just our climate. And so I'll use the example of food production system here. So you get different climatic hazards. So here, for example, drought and heat. And so this directly affects our food supply. So it affects our soil quality, it affects our crop yield and the quality of our crops. And all of this ultimately leads to changes in food price and essentially malnutrition. Separately, changes in Earth's temperature, so increases in temperature, can affect things like where pests like mosquitoes can inhabit. And so if you get an expanding range of where mosquitoes or other disease-carrying insects live, you can get an expansion of infectious diseases. And this can be compounded by the impacts of something like malnutrition, leading to even worse effects of infectious diseases. So all this kind of goes to show that there are these real cascading impacts that don't just impact our climate, but impact quality of life and human well-being. I'll give one more example of these cascading impacts in terms of air pollution and air quality. So in 2021, air pollution was the 2nd largest risk factor of deaths. So it caused 8.1 million deaths. And so it's really important to think about how climate change is going to impact air quality. And so I'll talk about just a few of these, but one kind of impact is that it can change the sources of air pollution. So something like wildfire that can emit directly particulate matter, ozone precursors, which are both really have negative impacts on human health. In addition, something like drought that can impact our vegetation, which acts as a sink of ozone, and can also increase our kind of the emission of dust, which is a form of particulate matter. And so here you can see that climate change is going to impact air quality negatively by increasing sources of air pollution. In addition, things like heat waves and increasing temperatures, that's going to impact the chemistry of our air pollutants. And so hotter temperatures leads to kind of faster, hotter chemistry. And so you get the increased production of secondary pollutants like ozone and some forms of particulate matter. And so I'll stop there and I'll pass it over to Shreya, but she'll talk a bit about how we'll actually think about quantifying these different impacts.
Okay, now with that, I want to move into understanding what really happens if we do not take any action to mitigate these impacts. So just to recap from yesterday, climate change is a tragedy of the commons. What this really means is that a few people who do these activities which cause climate change, and they reap the benefits from climate change, but the harmful effects are felt by everyone. And the analogy that was given yesterday is like you can think of a farm and a couple of people who own certain animals, and they get all the benefits from the animals, but the degradation of the land that takes place because of those animals grazing is actually felt by everyone. Now, many anthropogenic activities lead to climate change, like you can think of the energy sector, the agriculture and food sector, the transport sector. And for this section, I'll take the example of the transportation sector to see what these emissions are and what these downstream impacts are. So the transportation sector, you can think of vehicles on land, like privately owned cars, trucking, the trucking system, and also ships and aircraft which are not on land. And most of these systems, most of these vehicles run on fossil fuels. These are hydrocarbons. And this is considered a hard to abate sector. This is because all the technology is currently running on fossil fuels, and it is very difficult to get the kind of technological improvements to really move to any other kind of fuel. So the kind of emissions we have from the hydrocarbons are carbon dioxide and water, and these are considered well-mixed greenhouse gases. So that means that if you emit it at a location, you can assume it to be well-mixed within a certain period of time. And then these are greenhouse gases, so they trap heat. You also have aerosols, and they can either scatter or absorb the incoming radiation, depending on the type of aerosols. And you have some other trace gases like nitrogen oxides, which are reactive, and they can either form other greenhouse gases or change the balance of other chemicals. So all of these lead to a change or an increase in the radiative forcing. What this means is it changes the balance of the incoming and outgoing solar radiation. And this leads to an increase in temperature, as mentioned yesterday, just to account for that balance. So this delta T, or the small increase in temperature, has some cascading impacts. And those are basically the negative outcomes of certain physical impacts. You can think of health and labor, like the risk of people dying from heat stroke, the risk of people working under unsafe work conditions, like that are outside the safe temperature limits. You could have problems with infrastructure, like an increasing energy demands for, let's say, cooling buildings. You could have a lot of cost to repair and replace certain infrastructure. You could have things like damages to the ecosystem. This is like flooding, sea level rise, loss of biodiversity, all of those things. Now, all these negative impacts can be monetized. What this means is they have a cost associated with them. I'll take one example here. This is for the first thing of like people, let's say, dying from heat stroke. And the way it's often expressed is using the value of statistical life. Now this can cause some confusion, the term value of statistical life. So it's not exactly assigning a value to one particular life, but what this means is the economic value, what is the economic value of reducing the mortality risk to certain people. And how this is estimated is by using surveys, asking people how much they're willing to pay to avoid a certain increase in mortality. So that is how the value of statistical life is determined. So here is a graph showing how, let's say, the estimated change in death rate would be for a 2-degree warming scenario that Lexi talked about in 2050. And we see that it really varies a lot by region. The tropical regions have a high increase in the death rate, and then closer to the poles, you actually have a decrease because some of these regions might lead to a decrease in people dying from, let's say, extreme cold. So not only are these negative impacts not equally distributed, the value of statistical life, which is the proxy that is used to estimate this, is also not constant in all countries. So the deaths and damages occurring from a certain emissions and temperatures, we assume that they occur over a certain period of time, actually in fact decades, because the temperature change stays for a couple of decades. And to get that to a net present value, which is like what it would mean at present day for these damages to occur, we use discounting. Now what discounting means is like how much, like I mentioned, how much we value the damages at a later time. And a high discount rate, like here of 3%, means that our society is valuing the present benefits much more than the future benefits. So this would mean that short-term projects would be incentivized more, and then long-term climate action would be less urgent, and this would lead to a lower social cost of carbon. On the other hand, you have a low discount rate, let's say a 1.5% example here. That means the future generation's well-being is given much more weight as compared to a high discount rate, and so this would justify certain investments in climate mitigation. And the accepted discount rate used today is somewhere in the middle, around 2%, which is around $185 per ton of CO2. So what this means is if there is a present emission of a ton of CO2, society will collectively pay $185 for the damages that 1 ton of CO2 causes, and this money is paid over a long time. So let's take a small toy example. This is just assuming 500,000 ton of fossil fuel emissions from any sector, and let's say they lead to a 1 million ton of carbon dioxide emissions, since the carbon is burnt in oxygen. And that leads to a very small and almost imperceptible change in temperature. It's around 10 to the power minus 7 degrees Celsius. But since the social cost is $185 per ton of CO2, the actual damages are around $185 million that the society will pay over several decades because of these damages. The second thing that Lexi also mentioned is the air quality degradation that is caused by different emissions. And in this case, you could think of nitrogen oxides, other volatile organic compounds, particulate matter, the very fine particles that are in the atmosphere, and other chemically reactive compounds like sulfur dioxide. And a major difference is they are not assumed to be well mixed in the atmosphere. So you wouldn't, like emitting them really depends on where you're emitting them and how much you're emitting. So to quantify that, we use chemical transport models, and Chris will explain a little bit more in detail. And basically, you could run these simulations with certain initial conditions of how much you are emitting, and depending on the background conditions in different regions, you could get what the change in the chemical composition is after a certain point of time. So similarly to the climate damages, air quality also has negative outcomes of certain physical impacts. So again, you can think of premature mortality due to diseases like asthma, cancer, other cardiovascular diseases. You could have adverse birth outcomes for people inhaling them at the time. And also things like missed work or school days. This is very common in areas where there is very heavy smog and it's not safe for people to be outdoors. And similar and analogously to the climate damages, you can also, again, monetize the cost of these damages. And again, we can use, for premature mortalities, we can use the value of statistical life in this case as well. So this is again a graph showing what the deaths were from outdoor air pollution at a certain point. This is in 2021. Again, we see differences. Certain countries, especially those that are densely populated or already have poor air quality, they have a large number of deaths as compared to other countries. And the second thing to keep in mind is the value of statistical life also varies a lot. And the value we use commonly is around $10 million. So the same example that I spoke about before, for a 500,000 ton emission of fossil fuels, we again have a very small increase in, let's say, particulate matter of 0.01 micrograms per meter cube. And from epidemiological studies, you could estimate that this leads to around 300 premature mortalities. This is only due to one component, due to PM. And because the value of statistical life is $10 million, you have around a $3 billion of damages that occur relatively soon due to these air quality damages. And so this is, at least in terms of climate and air quality, the damages caused due to a certain pulse of emission at a certain point of time. So the thing to focus on here is that not everyone is affected equally. Like in terms of adaptation, you could think of economically stronger societies. They will be able to have the energy expenditure to, let's say, cool their buildings, etc. Coastal communities or communities living in very hot regions are going to be the ones that are maybe going to lose their homes and have other problems. And for climate impacts, these future generations are going to bear these damages from emissions that are occurring today. In terms of air quality, again, people who are working outdoors and in manual labor jobs are going to be much more exposed to these pollutants. They're the ones going to be really breathing them in. Similarly, for people living in certain regions like near highways for the transportation sector or other regions where there are a lot of industries present are more at risk. And similarly, people with limited access to healthcare, because even if you do get a certain disease, it really matters whether you have access to healthcare, really dictates your outcome. So this is an overview of the downstream impacts, and I'm going to pass it over to Chris to see how we project climate impacts.
Thank you. All right. Thanks so much for following along with us. I'm now going to give us a tiny break from the talking and actually give a little activity for all of you. Not too much of an activity, but turn to your neighbor and discuss for 2 minutes. You know, we've been talking about all of these interesting and impacts of climate change, and talk about how you would go about tackling the challenge of trying to project these future climate impacts. So we're going to take like a minute or two just to do that real quick, and then I'll call in some people. Don't be shy, no one's going to bite. No, this is an activity. All right, everyone, start wrapping up those conversations. We're going to come back in about 15 seconds. Cool. All right, everybody, let's bring it back together. Cool, cool, cool. Is this thing working? All right, we're gonna come together and discuss some of these answers now. Thank you for making my job easy. It was I could hear lots of interesting conversations going on. So this challenge of projecting future climate impacts. So what are some ideas? Feel free, raise your hand. We have mic runners all around the room. So any volunteers to get us started off? I can stand here and stare at you all day. Really? No ideas? We had so many interesting conversations. All right. Popat, I'm going to cold call you to get us started off. Paul, can you bring him a microphone?
In my way, the transportation section, you can switch into the electric vehicle, and that will be helpful for the CO2 carbon dioxide, emissions and all that things. And maybe the more tree you can plant in the cities like a garden like that. That is also helpful for.
Cool, nice.
Yeah.
Awesome. Keep your mic back. Cool, thanks so much for that. Any other responses on this problem of projecting future climate impacts?
It looks like that first that because that is a tragedy of the common problem, we should really try to agree to tackle it to start with, however way, because if only some people do it, then it negates the effect of what other effort we may put in there. And those goals will not be reached, and people will try to live with the worst.
Awesome, thank you so much. So that's a really good comment to tee us off for this next bit of the conversation, because there is this question of how do we all agree on what's happening and agree on what we're going to do about this problem. And so I'm going to pivot a little bit from the impacts of what we've been talking about and get to the how of how we get to those impacts. And the big thing that we use to get these impacts is through climate models. So again, throwing up our favorite picture of our friendly box model here that breaks down the Earth system into really three concise components: the atmosphere, the land, and the ocean. But the real Earth system is much, much more complicated than that. And now I'm going to show just how complicated it can get really, really fast. Don't feel too overwhelmed by this, but there are lots and lots of components of the full Earth system. So first, this atmosphere actually gets broken up into many, many, many different pieces. It's responsible for our water supply. This is where we have extreme weather events that we need to be accounting for. This is where we account for those aerosols and atmospheric chemistry that have been mentioned a few times. We can break the ocean into lots of different processes, one of the big ones being these modes of variability. If you've never heard that term, that's okay, but I think a lot of people in the room have probably heard of El Nino, which is one of the biggest modes of variability that we care about for its impact on us and on the water cycle. We also have the land system, and now this is where human impacts come into play when we're thinking about how do we actually model these future climate outcomes. So you need to model how we change the surface of the Earth. It's called land use change. So if you're going to go chop down a whole section of rainforest, what sort of albedo effects does that have, like we talked about yesterday? Also just the general dynamics of plants and vegetation that make the carbon cycle breathe, like we saw yesterday. And then the final piece here that's missing from our very simple box model, but it is super, super important, is the cryosphere. So a lot of Earth's energy balance especially is dictated by what's going on at those polar regions. They reflect a lot of incoming light, and they store a whole bunch of water, which is why we care about it for things like sea level rise, for example. So now how do we actually go about building one of these climate models if we want to try to encapsulate all of these different processes? So the first step is that these full-scale climate models are made of discrete grid cells, what we call them. So a computer, though our experience of the climate, our experience of the world is continuous from moment to moment, computers can only work in discrete blocks of memory. And so you have to do what's called discretization. And so this would be a very, very coarse discretization with this box model. There's only 3 of these grid cells. You're trying to account for the entire planet with just one grid cell for the atmosphere, one for the land, and one for the ocean. But when you want to move to a full-scale 3D representation of the Earth, we have to break this into many, 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 many more grid cells to start. And so you can see there, we're looking at just a slice of the Earth kind of over North America. And the way we do this discretization is we break up the Earth into these cubes generally that are kind of broken up by latitude and longitude levels, for example. But that would only get us so far if we had these squares over the land. So we need to model the ocean and the atmosphere as well. So we have to make these squares into 3-dimensional cubes that go all the way to the top of the atmosphere and all the way to the bottom of the ocean, so that we can model all of the different processes that are going on at these different levels. Now, this slide isn't meant to scare you. It's just meant to give a little bit of an appreciation for the very, very hard work that goes into making these full-scale models, that go into making these projections and understanding what's going to happen into the future. So around the world, there are dozens of these research centers that are these research modeling centers that their whole purpose basically is to develop these climate models. And so you've got teams of PhDs and postdocs and professors working together to model all of those different aspects of the system. You might have a couple people working on the atmospheric chemistry. You're going to have a team of 10 people working on the ocean, all sorts of stuff like that. And for those of you who have been in a physics class recently or fluid dynamics or something like that. Basically, the goal of what these research scientists are doing is to simulate the evolution of these different conservation equations. So don't feel pressured to memorize this. It will not be on the quiz. But the goal of these climate models is to discretize these equations and then solve them, which gives us things like temperature, pressure, relative humidity, winds, et cetera, et cetera. Basically, any sort of variable that you could see outside on any given day, these climate models can simulate them. Now, you might be asking, why do we have dozens of these modeling centers instead of just one? Why don't we just pour all of our resources into making one really, really big, really, really great model? And well, logistically, that would be a nightmare for anyone who's worked in any kind of project management before. But practically, there are thousands of design decisions that go into making one of these climate models. I've listed a few here, such as this grids, for example. So we talked about that discretization on the last slide that was using those nice even cubes, but there are some really interesting, funky things that you can do when you're making this grid, one being this yin-yang grid, which fuses two half donuts together to make the discretization, or this cubed sphere grid that takes a cube and projects it onto a sphere, which is kind of a funky concept to wrap your head around. But none of these are strictly better than the other, but they all lead to kind of different effects when you run these simulations forward in time. And so we need lots of these modeling centers to try to test different combinations of what actually is going to give us the best, most accurate results for a model. Now, these models have progressively become more complex over time. So here I'm just showing a few examples. I'll go through this fairly quickly for the sake of time. But back in the 70s, all we could model basically was our emission of some greenhouse gases, pretty much only CO2, and we could model very limited amount of processes such as like precipitation, basically. Then we added the land and we added some ice to try and account for some of those cryosphere feedbacks that I was talking about. And then we got to the IPCC. This FAR and SAR would be the first and second assessment reports, so this intergovernmental panel on climate change. And as we moved forward in time, we added an ocean. Then the ocean got deeper. We added volcanic activity, as well as more human activities. And then this brings us sort of closer to our modern state of affairs, where we now have an interactive carbon cycle, so the vegetation actually breathes in these models. We have atmospheric chemistry, that sort of thing. And I've talked a little bit about that discretization because it's one of the biggest components, and this is why there's, you may have seen in the news that there's always a little bit of uncertainty around climate change, and we'll get into that more in just a couple minutes. But part of the reason where that uncertainty comes from is because these models are computational beasts. They're unlike anything that most people have ever heard of. If you think of something on the scale of like a ChatGPT, a lot of these models are going to be orders of magnitude more expensive to run than one of those models. We're talking weeks to months on supercomputers just to predict something at, oh, my bad, this 500-kilometer resolution, or that's how it used to be, but now we've moved up and we can now simulate things that are in the order of 100 kilometers of resolution. But you'll notice that's still far too big to get down to, and even an individual city generally is not resolved in these climate models. So now there's these big high-resolution efforts that are trying to get down to kind of the 10-kilometer scale and continue making things higher fidelity so we can get more confidence in those climate projections. And so I gave a little bit of a teaser for this already, but again, going back to this idea, why do we have dozens of these modeling centers? It's because no single model actually gets everything right. When we have dozens of these different design choices, it leads to a lot of uncertainty in the actual model structure that you're working with. And so Shreya will take over in a moment to talk about these other lines, these other colors over here, but for now we're just looking at this blue line, which is if we're projecting precipitation out into the future, because of these different design decisions we've made, there's actually going to be a spread in what the models predict the precipitation is going to be, simply because one is using this yin-yang grid and the other is using this cube sphere grid, for example. So what does this look like in practice? Here's a bit of a toy example just to prime you all. We use a strategy called ensemble modeling to try and get over this issue, essentially. So if we're projecting temperature out in the future, the y-axis is temperature, x-axis is time. These blue lines are going to be individual models, so different grids, for example. And that black line is going to be the ensemble average between all of these different models. And so we do this because we found that in practice, no one model gets everything right. But on average, if you take the average over a bunch of these models, they actually get pretty close to what you see outside. And here's a real world example of that. We're going to walk through this kind of slowly to make sure that, we're going to walk through it piece by piece to make sure that everybody's on the same page. But first, this red line, this Hadkrut data set, is essentially observational data. So this is the temperature that we've seen outside. We've measured it with satellites. We're very, very confident in that sort of projection there. Now, all of these different colors are future emission scenarios. You don't need to know the specifics, but just know that the number at the end there corresponds to some metric for warming. So 8.5 warms more than 2.6, and you can see that at the right side of the graph there where this pink line is higher than that green line on average. So again, from our toy example, we saw that each of these individual lines is going to be the projection of an individual model, which then gives us some sort of projection uncertainty as we go out into the future. So there's a range of possible outcomes for each of these scenarios. However, what I want you to take note of is that all of the models are kind of telling you the same story. Yes, there's a bit of a spread, but on average, that pink one is going to be more warming, lead to more warming than the blue or the green scenario. And that's really important as we're trying to make policy decisions based off of what could happen in the future. So these on this ensemble format is exactly what's used to inform our climate assessments. So we've referenced some of these graphs from the IPCC 6th assessment report before. And what's going on here is that underlying this, there is exactly that same sort of ensemble modeling strategy. So there's 20 or 30 climate models that are running all these same scenarios, making these same predictions, and then they take the average of all of those results, and that gives us these pretty maps that tell us that, the Arctic is warming much more than the rest of the world, regardless of which sort of scenario you're in, and that precipitation over the Pacific is going to increase, likely on average. And with that, I will pass it back to Shreya to talk more about uncertainty.
Thank you.
So the second type of uncertainty that I'll be talking about is briefly a recap from yesterday, which is the internal or unforced variability. So this is the orange line that you can see on the graph, and it's mostly caused due to the natural variation of the climate system that redistributes heat. So this causes, let's say, the El Nino, or it causes things like volcanic eruptions. And when you follow it along different years, you see that in the short term, it does dominate the total amount of uncertainty. But in the long term, since there is no global energy imbalance, it actually becomes a very small portion of the total uncertainty in the long term. So that is on the second type of uncertainty, which is internal variability. The third type of uncertainty, or the scenario uncertainty, the one shown in green, is the one that actually dominates over longer terms. And this comes from not knowing how humans will behave over a long time. So we are uncertain about several decisions, like how much fossil fuel will be burnt in different places, how fast will different types of clean energy scale, and what kind of climate policy would be there for how long in different regions. And this is the thing that actually causes a scenario uncertainty, because we are uncertain of what future will actually materialize. So that leads to the Coupled Model Intercomparison Project, or CMIP. And this establishes some common experiments for different climate models, like the atmospheric, land, and ocean models. And it compares results and assesses the strengths and refines simulations. And it's run in many phases. The current phase is CMIP 6, which is the 6th phase. And what happens is it's like a controlled experiment where the physics of the models is roughly constant. We have these different emission pathways for the different scenarios. And all the outcomes are compared across different models. And we try to understand what the spread of all the models are. So like I mentioned, we are unsure of what scenario is going to actually materialize, but we can kind of group them into 5 different shared socioeconomic pathways. And we can visualize this on a 2D graph as shown. So on the x-axis, we have challenges to adaptation. And on the y-axis, we have challenges to mitigation. So you can think of this as if climate change causes something like sea level rise, the mitigation action would be to avoid that the negative outcome of sea level rise, and adaptation would be, let's say, building a seawall to adapt to the damages caused by sea level rise. So this is what the 5 scenarios look like. On the bottom left, we have, and they're numbered from 1 to 5. On the bottom left, we have SSP1. This is basically marked by a lot of international cooperation and sustainable development. and there are minimal challenges to both adaptation and mitigation. And if you go on the diagonal towards the top right, we see SSP2, which is like a middle of the road scenario. So this is how like a business as usual case where there are moderate challenges to both adaptation and mitigation. And further, SSP3 is like the highest challenge to both adaptation and mitigation. And this is marked by a lot of barriers to international trade, high amount of inequity. And then SSP4 and 5 are on the other two axes of if there is more challenge to adaptation or mitigation. So to sum up the part on uncertainty, uncertainty does not mean that we don't know enough to act. We are certain about a lot of things, like the direction of warming, the major impacts and the downstream impacts that the warming causes, and we are certain about the fact that this is caused by humans, or this is due to anthropogenic activities. The only uncertainty is about knowing exactly how much, exactly how fast, and exactly where these changes are occurring. And since these damages are going to keep occurring from now and for decades later, the policy choices today really determine what futures we are going to make more likely among all the possible futures. So to summarize Climate Science 102, climate change can impact a variety of both human and natural systems. Natural systems are like drought, etc. Human systems degrading, causing damages due to air quality, food insecurity. And we can quantify them using several measures or proxies like VSL, discounting for certain things. To project future climate scenarios, we use computational models. And you can think of this as a three-dimensional representation of the Earth system. And you can calculate quantities like temperature, pressure, humidity, and other derived quantities. And since no single climate model can fully represent all the physical impacts correctly, we employ ensemble modeling, which means model several different scenarios with several different models. And in terms of uncertainty, we look at three types of uncertainty. Model uncertainty, which comes from representation of physics. Scenario uncertainty from uncertainty in how humans will behave in the future. And internal variability due to uncertainty from natural cycles in the climate system. So we come to the end, and we are open to questions.
Thank you. I think that SSP section at the end may have started to answer my question, but I was curious about how many of the models consider human systems, or like political systems, as intrinsic to the climate system versus extrinsic. You had one bullet point in there that suggests maybe we're intrinsic to some models, but how common is that to consider? For example, I'm thinking now, as temperature rises, that increases political and social and psychological stressors that moves us towards short-term thinking, moves us towards greater inequality, which leads to greater mistrust, and so treaties break down, and that leads to more emissions, which leads to more warming. So you've got these lots of feedback loops like that. Are those usually included in ensemble models, or how do you think about that?
So that's a great question, and the short answer is that climate models are too slow and expensive to include the human system at that fidelity that you're talking about. And so in practice, we use these SSPs because they provide, we call them like storylines, which is kind of along the lines of what you're saying, where you can tell a plausible global economic story that leads to this level of emissions, this level of warming, that sort of thing. On the other side, there are folks who, we can talk more offline during the break, but here at the Center for Sustainability Science and Strategy, we have a general equilibrium economic model that we actually couple to a smaller climate model, so something that we can run, so we can try to understand how those feedbacks work, more so than with these full-scale, very expensive models. Cool, thanks. Cool. Well, if there are no
Yeah.
other questions, we can go to the coffee break. And thanks so much for your attention for this hour.